Hello guys, my name is Arun and welcome to my channel. This series is a series of tutorials on Advanced Fortran programming. Now in this tutorial, I'll be explaining you guys how to invoke OpenMP procedures in Fortran. Now don't get alarmed. As I mentioned in one of my previous tutorials and one of my last tutorial in the first series, the basic Fortran tutorial series, OpenMP and Fortran combination will be a separate tutorial series, and I'm planning of that in some time. Okay, this will be just a demo of how OpenMP can be used in Fortran. Okay, now what is OpenMP? Well, OpenMP is one of the two kinds of parallel programming paradigms available so far. Available in large scale. Okay, this is more of a procedure shared memory procedure wherein you create a lot of special subroutines and functions which does which kind of tells the compiler to split the job of your code, okay, among different processes and run them simultaneously. Okay, if as of now, just take it into consideration that OpenMP is a method through which you can make your program run in several processes. Okay, now there's a small motivation for it. I'll just give you guys an example. Okay, now if I were to okay if I were to open my system monitor available in Ubuntu. Okay, see, as I mentioned to you guys earlier, okay, let me just keep this together. Okay, as I mentioned to you guys earlier in one of my tutorials, okay, my laptop is I'm using my laptop for all my tutorial series and all. Okay, my laptop is an Intel i7 third generation processor. Okay, and it's since it's i7, it's a quad core processor. But the interesting thing is each of my four cores have two hardware threads. So what does this imply is that I have 8 processing units in my laptop. Okay, so each of my core behaves as if they are two separate cores. So because of that, I have like 8 cores advantage, and each of these cores has a processing capacity or speed of clock speed, whichever you call it, of 2.3 gigahertz. That's pretty interesting. Now the point I'm trying to make here is that you see, at any instant I have 8 of my cores running, and at the same time 8 of my cores running at the same time. Okay, the number of processors you have at the background in my system are these. I have like so many processes running. The point is, what happens is that at any instant you have like, let's say there are like 50 processes over here. At any instant, any fraction bit of a time, okay, only 8 processes can be run in the system at every fraction of a second. Okay, in my system only 8 processes can be done, and each of these processes will be done by one CPU. Okay, and now what happens is that but since there are only 8 processes, but how are all these managed? It's simple. That's where your RAM comes into the picture. What your processors do is that they concentrate on a certain job for a very small period of time, and then keep it on hold, take some other job, work on it, keep it on hold, take some other job, and so on. And once in a while, the processors swap the jobs among themselves, so that no job gets concentrated by a single processor all the time. Okay, now whenever you run your program in Fortran, what happens is that you will be running only you'll be using only one core to its fullest peak. Okay, now in parallel programming, what you can do is that you can make your multiple cores run the same program simultaneously. When that happens, what happens is that your time taken for your job reduces substantially, and that is the entire paradigm of parallel programming. Okay, Now we're going to look at that over here. And I mean, if you don't get this video so far, if you don't understand what we're going, okay, let me keep this aside to give you guys a demo. This will be useful, trust me. Okay, now I'll just walk you guys through this tutorial, walk you guys through this. Okay, yeah, fine, I'll just walk you guys through this program, but trust me, officially the tutorial series is over. This is just a demo tutorial, that's why I wrote this is a demo. If you understand this, it's good for you. If you don't understand this, don't worry, you don't have to worry about it and break your head about this. Okay, just don't worry, just understand. Okay, now what I'm going to do is that I use this module called as omp_lib. This is nothing but a module that contains the Openmp subroutines in Fortran or in Fortran. Okay, and then I set n to be 1000, which is a parameter. Okay, and then I set a variable called as numthreads to be 4, and which is actually an integer. But the funny thing is, unlike these, I have written this in with the comment with a exclamation sign followed by $sign. So you might be thinking, hey Arun, shouldn't this line be excluded? Since you wrote an exclamation symbol, shouldn't this line become a comment and get excluded or ignored? Actually, not. It does not, because though we have a exclamation symbol over here, the presence of the dollar next to it makes this a special kind of a statement called as a preprocessor directive kind of a statement. Preprocessor directive statement. So what happens is that whenever the preprocessor statements get activated, whenever certain flags are used. And what does a preprocessor directive do? It's simple. It just tells the compiler directly to do certain jobs at the lower level. When you are creating when this program is executed by the compiler, it produces an assembly level language or a machine level language depending on the system you're working with. Okay, and what does each statement has its own set of machine codes which gets generated. But what does these do is that these tell the compiler to make modifications in the assembly code or the machine code in such a manner that certain features are tapped in. Okay, that's the simplest way I can put it. Okay, and I create 3 matrices A, B and C and 3 indices I, J, K. Okay, T1, T2 and EP are just variables for finding or for understanding how much time it took for processes to actually do the job. To do the job and all. Okay, if you guys remember the timing in Fortran tutorial I made some time ago, I'm going to use the same thing over here, and I'm writing this entire print statement in front of exclamation dollar symbol. So what happens is that when Openmp is active, this statement gets executed. When Openmp is inactive, this statement will be just ignored. Similarly, this will be ignored when Openmp is inactive. Whereas when inactive, this statement gets printed, and when Openmp is active, this statement also gets done. What this subroutine called omp_set_num_threads or omp set num threads, what it does is that it just tells the compiler to make the number of processes available. If num_threads is defined at the top, it can be any variable. I just set as num_threads, but it can be numprocs or any variable. Okay, if this is set to be 4, it tells the compiler to make ready 4 processors to do the job. If you set this to be 1, it just tells the compiler to make only one processor available to the job. And if it's 15, it'll take 15 depending on the case. Okay, and that's why I made a comment here. You set the number of processes to be used, and then A matrix is set to be a 1 matrix, and 0 B to be in these statements I set B to be an identity matrix. Okay, and C to be 0. And what I do is I call the CPU timer here and I close the CPU timer here. This loop takes care of the matrix multiplication. The resultant multiplication of A and B are stored in C, and what I do is that I just invoke a parallel do loop statement available in Fortran, Openmp and Fortran over here. Okay, I start the parallel do statement and end the parallel block over here. Now what it actually does is that when this block is being invoked, this entire do loop, this entire nested do loop is split accordingly among the processes you take, and each of the process do a certain part of it. For example, if n is say 1000, then you have like 1000 iterations for the variable I. So if that being the case, the maybe like if there are four threads, maybe the first thread might take first 120 first 250 iterations. Second processor or a thread here takes another 250 iterations. Third one does another 250, and the fourth one does another 250. So if you guys look at it, all the processors will share the workload of this 100,000 iterations over here. Okay, but the advantageous stuff over here is all of them will take the job simultaneously and finish the job simultaneously. So as a result, if this entire loop takes like 10 seconds, because of the sharing, you might get this entire thing done in 2.5 seconds if you have like 4 processors. Okay, I'll just show you guys visually how it works. Okay, and then I call the CPU timer here, and what this does is that it finds the time over here and finds the time over here. The difference between these two gives the time taken for this entire matrix multiplication block to finish its job. Okay, and then EP will give you the time taken for the matrix multiplication, okay, in seconds, and then it gets printed over here. If you have done this in Openmp, what you have to do is that you just have to divide this by the number of threads, okay, or else what happens is that it will just show what happens is that it will just add the time taken for each and every processor which split the loop in this program, and adds their time and gives the cumulative time, but which may be misleading, which will be very misleading. But it's not a big deal, but it may look a little counterintuitive. And this is if you want the results to be as accurate as possible, this is not valid because in some cases the threads may not be evenly distributed with load. Some of the core or processor here might take a little more job and compared to others, something of that sort. So there may be an up and down. But assuming for this kind of a case, you can fairly straightforwardly assume that you might take equal load sharing will be kind of equal. So that's it. Okay. Now with that, this program is over. So what I'm doing is that I'm just doing a quick review. I'm setting the number of the dimension of the matrix to be 1000, n to be 1000. I'm importing the Openmp subroutines here and defining the matrices A, B, and C. A is a full unity matrix with all its value 1. B is an identity matrix. C is set to be C is a 0 matrix. I call the CPU timer here to start the parallel program start a timer before the parallel programming option. Okay, and use the timer to end the time note the time at the end of the parallel programming option with these with the CPU underscore time subroutines. Okay, and I call the matrix multiplication operation between these two, and enclosed within OMP parallel do, which splits this entire loop between the processes. Okay, and on the top I set the number of processes to be used. Okay, and then I just calculate the time taken for this entire process, and then do some arithmetic to adjust for the threads under the threads used, and then prints the same. Okay, now to run this, what I done is that I written a shell script, but it doesn't matter, you can run this from the terminal itself just like in previous tutorials. But I'm writing this in a shell script. Okay, the major things to be concerned is that I will show you how this works in serial as well as parallel, how this code which you have written here, okay, can be used serially as well as in parallel. Okay, what you do is that when you compile the code normally with the -c flag, and then use the -o flag to build the executable and run the executable just normally. Okay, you'll be just doing a normal regular serial execution, serial compilation. When this is done, all the OpenMP stuff, that is such as this line, this will be taken, but it won't be, it will be ignored, so not a big deal. Okay, this line, this line, and this statements, all these statements in this light blue color will be ignored. It will be taken as a comment and will be ignored by the compiler when these lines are used. Okay, the reason is because the OpenMP flag is not present over here. Okay, so when you execute this, this will be just a serial execution. That's why I just named it as SCR underscore matmul, meaning serial matrix multiplication execution. Okay, and now how to run this in parallel? It's simple. You just have to repeat the same syntax you use on the top, but the vital procedure is this compiler flag over here. Okay, minus f openmp. If this flag is present, now this flag will tell the compiler stating that okay, I'm invoking a parallel openmp modules over here, specified for Fortran. Okay, take that into consideration and run accordingly. When this is taken into consideration, all these light blue statements over here will be taken into consideration, and they will not be ignored. They will be treated, and the result gets run nicely. Okay, now let's build this up. Since these are the same folder and I made this shell file executable. Okay, I just execute this. Okay, it's running in serial. But there is a small issue. It just says that there is a segmentation fault. I'll explain what happens. Okay, and just to tell you guys, okay, just keep this in mind. And look, if you guys look at this graph over here, the CPU history usage, you just see a spike over here, a spike in the green color. What the spike is actually, that is the third CPU of my computer started the job. And if you guys notice, if you guess it right, okay, when my Fortran program started the execution, okay, my third CPU took the job and did the job over here. Okay, now I'll explain you guys what the segmentation fault is. See, sometimes what happens is that when you run parallel programming stuff, or when you run programs with matrices whose sizes are very large in nature, especially when your RAM is limited. Like my system has 8 GB RAM, but that's okay. But in certain systems, or if you're not using supercomputers and all, what happens is that you'll have some memory restrictions. Like there's a limit on how much memory you should use and stuff. So to rectify that, to understand what's going on, what I've done is that I just open the terminal directly in Genie. Okay, I just clear this up. Okay, I just have to see what this Q. You just type U limit and then type -s and to press enter. Okay, if this value is not unlimited and it gives us a finite value, then it shows that the amount of memory allocated for intermediate processing before the RAM is little less in number. Okay, now this might cause you segmentation fault, because whenever a program runs, segmentation fault error comes when your compiler is trying to access memory for which the memory is not allocated. Let's say you have to run this program, you have 20 MB of data allocated in your RAM. Okay, and then while compiling it, when you execute it, you access little more than 15 MB. Then as per the compiler initially allocates only 15 MB, but you need 20. So what happens is that the remaining 5 is not available. So what you get is it tries to access memory from data from some location whose location is not available in your part of it. Which might have been used by some other program, or in the region outside the region allocated for your memory. Then that's what you call a segmentation fault. That is, you're trying to access a segment. The program tries to access a segment which does not have the right because of the memory allocation. Okay, Now this can be avoided. When what you have to avoid this, what you have to do is that you just have to type ulimit new terminal -s and then type unlimited. Okay, and then press enter, and then you try the same thing. It should, if it's unlimited, what happens is that it just makes sure that the memory gets allocated as much as it needs. Okay, now now this terminal has the ulimit feature set in, so instead of running this directly from using F5, it's better to run this from here. Okay, suppose every time if I run F5, I'll get the same error stating that same error stating in the compiler stating that this ulimit is not set. I mean the segmentation error and stuff. Okay, so what I do is that I just type bash and then star dot sh. Okay, run this. Now watch. Initially you will be running the serial part of it and then the parallel part of it. When you run the serial part of it, among these 8 cores, one of the core will take the job and you'll notice a spike. You'll notice a spike in full capacity. And then when the parallel programming regime starts, you'll notice 4 spikes in the history record over here. And then to indicate the same, you will have a small spike in the RAM memory over here. Okay, look for this pink line over here. This is the RAM memory, which will also have a small plateau like spike for a short period. Have a look at that. Okay, there's a reason why I kept it, and you will appreciate this better if you have a visual demonstration. Now watch, running this in serial. Okay, okay, now what just happened, I'll explain you guys. See, this red spike is because of the serial execution. Okay, this red spike is because of serial execution. This red is corresponding to the CPU 8. So when the serial execution is done, CPU 8 does the first job, and then as and when it closes, the remaining 4, 1, 2, 3, 4. These 4 are because when the fourth. These are because when the parallel execution starts. In our program we used 4 threads, so it's invoking 4 threads. Okay, okay. Let me put this as 6 threads. Okay, let me put this as 6 threads, and let's see what happens. So ideally, when the parallel programming when 6 threads are used, you should see 6 spikes in the data. Now let's see how this goes. Okay, running in serial over here. Okay, now watch. When you guys run this in serial, this is what happens. You can see almost 6 spikes over here. This initial blue one, light blue one, which is CPU 4, took the first job, and afterward when it fell down, the other process took in charge of it. Okay, there's a procedure. You can make all the 8 processes run as well, right? All the 8 threads and run as well, and watch. Serial, running in serial. Okay, parallel threads done. Now if you guys look at the spikes, now this is very much evident. Initially the only one processor used. Now since we use 8 threads, you're using all the 8 cores to do the job. So you see, we are having control to manipulate the number of processes to force the process to run your job accordingly. Now this is the advantage. This is the beauty of parallel programming. Okay, and if you guys notice, the time taken for a single loop, time taken for the entire matrix multiplication by a single processor is like 4.8 seconds, whereas when all the 8 processors are used, it just dropped to 1.34 seconds. Okay, now let's make this to be 2. Okay, just 2 processors. Okay, and if you guys notice, you will see only 2 spikes over here. If I were to run this again, watch, running in serial. Okay, so what happens is that the orange one spiked up Okay, the orange with the CPU one spiked up, and when two threads are used, you see only two spikes, the red one and the orange one, indicating that only two processes were used. And if you see, guys, notice the time taken for the when two processors when compared to the one processor is approximately half, not exactly but approximately half. So you see, with the number of processes being used, you get the size. Now this will be very much evident when the number of the data sizes, when the time span between these two will be very much evident when you have a large number of data sets. So instead of 2000, instead of the matrix being 2000 cross 2000, 1000 cross 1000, let me set this to be 2000 cross 2000. Now the matrix will be uh, 8 times larger in memory, kind of. So this will take a large time, but you will notice a very large drop. So what I do is that I just take 4 processes again for my consideration and run this. Watch, when I run this in serial, now the lag will be less, and you can see one processor will shoot. Right now the job is being swapped between processor 7 and 8 continuously. They just take some time and split the job, but still at any instant only one processor is active, either 7 or 8 is active, and you can see clearly right now that processor 1 took the job and it worked out, and it is working out. Okay, and now when 4 threads are used, you can clearly see two more spikes over here, and 4 threads are being used. And then after the entire, there's a kind of a lag over here, but that's why you're getting this. But ultimately when this settles down, okay, there has been some issues, but if you guys notice, you see the time difference it takes. When one processor use, it takes like 36 seconds, whereas when 4 processors use, the time drops by 13 seconds. Imagine you have a very very large amount of calculations. This is just a simple matrix multiplication, but if you just have a very very large amount of calculation, imagine the amount of time you can save by using parallel programming. Okay, here you might not have an exact divisible by 4 and stuff, because along with this process there are like 100 other processes running at the background, and the operating system also is running and stuff. So this you may not get a proper load share over here. At the same time, the loads are symmetric for the processors, but in certain times it may not be symmetric and stuff. The CPU may not be available and stuff and all, so you may not get a proper divisible by 4. But you can approach that when only certain job is done. Okay, now to show you that there is a change in there is a RAM. If you want, if I were to set this to be 4000 or something, this time will just exponentially increase. The RAM will also load up in memory, so I didn't want to do that, but anyway, I think you get the point over here. So if you guys are already good in Fortran, or if you are able to come all the way to understand large amount of Fortran, the next interesting point will be to invest your time on Openmp. And I strongly recommend Openmp or MPI procedures. I'm not giving an MPI demo over here. That's a little more tricky, and it's not easy to explain in a very short period. Very not easy to explain. Okay, it's a little. You can explain that, but it's a little tricky. Okay, and that will be a little too far-fetched for now. Okay, if you guys are into computational domain, where you have to do a large amount of scientific computation, scientific calculation, and high performance computing, calculate large number of values, especially if you guys are from atmospheric or oceanic sciences departments, or quantum mechanics departments, or astrophysical simulators. Somebody who simulates simulate the astrophysical fluid flows and stuff, how stars and generate and stuff of this sort. I strongly recommend you guys learn OpenMP or MPI or any other parallel programming methodology available. You will find it very very useful. And if you guys are running stuff in supercomputers, then OpenMP or MPI are the best way to go about with them. That's all I have for you guys in this tutorial. Thank you guys for watching, and I'll see you guys next tutorial. And that will be a wind up tutorial as to what to be done and what to be done and where to go beyond from here in Fortran. Thank you guys for watching, and take care then.